So welcome to Lecture 2 on Spacetime. Technically what I call Minkowski space is really just one model of such a space. So I think of it as R4 paired with a particular metric. But I should say, if such a space really existed in nature, then it will be in bijective correspondence with M as defined below. And I would point out that, in fact, that bijective correspondence with M really amounts to the existence of an inertial observer. And so the existence of inertial observer really, what's going on there is what Carroll describes in terms of setting up a coordinate system, right? Being able to measure distance and time at different points by a systematic, he describes a systematic means for setting up such an inertial observer. I won't get into that. I'm just saying that that's a physical assumption that you could actually do that in, in space itself, in physical space. Now, mathematically, you can describe that by simply saying your set is R4, right? R4 is set up such that it has 4 coordinates like that, and that's it, right? Now, the points in four-dimensional space-time are known as events. An event is a time and a place, all right? A time and a place. And the interval between two events, let's say x1 upper mu and x2 upper mu. So this notation here, I mean like the collection of x10, x11, x12, x13, and likewise for x2. Well, the interval is given by the Minkowski metric acting on this right here, the change in x mu, which I'm saying is x2 mu minus x1 mu. I'm going to call that the increment. I don't think Carroll calls that the increment, but I'm going to call it the increment. You might call it the displacement. I'm going to call it the increment just to give it a name. And anyway, so that increment is the difference of the coordinates, time, and space, space, space. And we're just going to call that delta x as a four-dimensional vector. And so the interval, which is delta s squared here, is given by the Minkowski metric acting on increment and increment again, which is given by this formula here. The transpose of that 4 vector times the 4x4 eta matrix times delta x again here. Let's look at the details of what that is. Let me slide this up here a bit. So, all right, so this is the interval, and it's given by this formula here. And so this is a fancy way of writing it, but all that really is going on here is you have minus the time interval squared, and then plus the square of, the time, well, I mean, change in x naught is the time interval, right? In the usual conventional language. And this is the displacement in x1, this is the displacement in x2, this is the displacement in x3, and you're squaring them, all right? So this would be like a like the last 3 terms are like the Euclidean dot product of a 3 vector with itself, right? But there's this minus out front, which is again why we're not getting a Riemannian metric. But this eta is just given by that, zeros otherwise, all right? And it is symmetric, it is non-degenerate, its determinant in fact is -1, so it's invertible. So it's symmetric, it's non-degenerate, it is a semi-Riemannian metric. So this metric has nice properties. Probably should make you some homework about that. There's some easy homework problems to do there. Let me think of them for you. But just anyway, to recap here, space-time has x naught equal to ct, right? C is the speed of light, right? And then x1 is x, x2 is y, x3 is z, where we use x, y, z as we usually do, talking about 3 dimensions. I think maybe we should call it time space, right? Time comes first. Now, most of Carroll puts c equals to 1. I'm going to try to leave c not equal to 1 in as many equations as I can get away with, just because I think it helps to see. But there will come a time where I'm just like, all right, fine, c is equal to 1, take our medicine, move on. All right. So, a little bit more formalism here. The increment between 2 events A and B we denote by delta x. I decided that A and B would be nicer because that way we don't have so many indices flying around. So like the change in the time part, the change in the x part, change in the y part, change in the z parts, the increment between these 2 events A and B. And so this is actually a particular instance of what's called a 4-vector. A 4-vector is just a 4-dimensional vector, and so we can define the Minkowski metric acting on 4 vectors like such. So Minkowski metric on VW, you get minus the product of the time components, and then plus, well, what you would identify as just the regular Euclidean dot product of the spatial part of the the 4 vectors. So here this is the time component. This is the spatial component. Thinking of x, y, z. All right. So this is already weird relative to like classical mechanics, of course, because our usual mechanics doesn't mix time and space like this. This is some formalism which is putting space and time on the same footing. Obviously something really different's going on here. So the Minkowski metric restricts to the usual dot product on the spatial parts. However, strictly speaking, as I was mentioning, G is not a metric or inner product sense. G of VV can be 0 and V is not 0 in some cases. Here's some examples of those. So these are the so-called null vectors I was mentioning. So like 1, 1, 0, 0, and so here I think I have put C equal to 1 basically, because otherwise I don't know if that comment even makes sense here, but anyway, 1, 1, 0, 0 is a vector, and when we feed it to the Minkowski metric, we get back out 0. The same thing happens for 1, 0, 1, 0 or 1, 0, 0, 1. These are all examples of null vectors, and I would point out that the null vectors above all correspond to increments formed by following the path of light from one event to another. All right. So the approach here in Carroll is essentially to define this interval to start with and to say that this is the thing that's physical. In other words, if you were to pick 2 different observers, right? If you had one inertial observer and another inertial observer, then the interval between events they would all agree on. So the interval is the thing we hang our hat on, and everything's based on hooked up to the interval. The interval is basic, all right? Now other treatments of special relativity derive the interval from looking at applying Einstein's axioms 1, 2, and 3 to particular thought experiments, then deriving what are called the Lorentz transformations, and then from that getting the interval. So this is kind of upside down to that. Starting with the interval and then seeing what does the interval allow. That's kind of the framework here. One of the things, of course, that the interval allows is vectors whose non-zero vector whose metric, Minkowski metric with themselves is in fact 0. Another way to say that is there are increments that are non-zero that nevertheless have 0 interval. All right. So the interval between 2 events, it could either be positive, negative, or 0. All right. And while it's hard to draw 4 dimensions, we can draw 2 dimensions. So if we suppress the y and z coordinates, then this is a standard like 2-dimensional space-time diagram. You can get a lot of insight from this thing. So we'll suppress y and z and consider only the x0, which is ct, and x1 equal to x. You can draw pictures like this, and let me just talk about a couple different trajectories, if you will. So what I'm saying is you got a particle, it starts at the origin, and it travels to either A, B, or C. Now, I said a particle travels to A, B, or C, but in fact only A is reasonable for a particle to do. As we study the physics more, we'll find out that A corresponds to a speed of that particle which is less than the speed of light. And so that the increment from the origin out to here is negative. So this is what's called a time-like interval, and on the light cone going from the origin out to D following x equal to ct, you see the speed of this trajectory is c. So that you're on the light cone, you have 0 interval. It's a light-like path. And then the interval from 0 to c, it's got a positive interval. That's what's called a space-like path. And so that would correspond to faster than light travel if you could actually do that. As far as we know, you can't. Um, all right, so again, here's the, to summarize. A is possible for a massive object, we'll learn. B is possible motion for light. C is impossible motion for a physical object. So let's talk a little bit more about that. Generally, objects follow paths known as world lines, all right? And for a massive object, the increment between events on a given world line should be time-like. So I tried to come up with one that was a little bit more interesting than just a straight line. So here I've got some particle, and it's traveling, and then it stops moving in the x, so it like kind of just pauses here, and at the origin at x equal to 0, and goes through here, and then it starts moving to the left again over there. And if I did my picture right, at no point is this line have a slope which is larger than 1. It's always got a slope, smaller than 1 in this picture. So that would mean that like the speed is always less than the speed of light. And so this is a plausible world line for a massive particle. You have to think about it as a local idea. You have to draw a light cone at each moment along the path, and sort of think about it from there. But anyway, more on that later, I suppose. And then, so of course, not all paths are lines. So just like we talked about in calculus, you need some notion of arc length. So here's sort of the analog of that. Proper time between events is given by minus the interval squared. And so for a path through space-time, aka world line, we can define the see, I'm calling the interval squared. Maybe I should. I don't know. I'm sorry, folks. Like this is. I called the square of s interval, and I think that's right. Oh, good grief! Shush. Quiet. All right. Google surveys trying to give me fake internet money. Anyway. So here is delta s. It's defined by this integral, like so. All right. That's for a space-like path. For a space-like path, this is the so like the direction of the path is given by the tangent vector to it, and so for a space-like path, this is going to be the interval of the tangent vector, and so that would be positive for a space-like path, which means that the square root we could calculate. In contrast, the time-like path, the tangent vector is time-like, which means that without the minus it's negative, so with the negative it's positive, and then you can integrate. And so that's the so-called proper time, all right? And proper time, if you specialize proper time to the frame of reference, which is co-moving with the particle, then proper time is actually the time which is experienced by the material particle. There are the words, material particle. So I would say this: infinitesimally, the interval ds squared is eta mu nu dx nu. This is a summation here over mu and nu. We'll talk more about that in a future lecture. And the square of the proper time is basically minus ds squared. That's what guides these constructions. Anyway, so he has a nice discussion of the twin paradox here, which I'll talk about briefly. And so if we think about, this is one of the standard, so like when you teach special relativity, a lot of people focus on so-called paradoxes, seeming contradictions of the theory, and this is one of those. So you have two twins, right? One stays on Earth and just sits there. The other one speeds out to Alpha Centauri and then comes back again. And then, so then the question is, what happens when you compare their journeys? And so this will just take us about 2 minutes to wrap up here. And so these we can compare, and you compare the time that's experienced by the twin just sitting on Earth versus the time of the twin who goes out to Alpha Centauri and back again. All right, and when you compare their times, let's see here. So the proper time experienced by ABC is it's just delta t basically by construction here. So A is 0, 0, the origin. C is delta t 0, so it didn't go anywhere. We're saying x equal to 0 is the Earth, okay? And then B, the middle one, is just at the halftime, all right? And so halftime is when Mr. Alpha Centauri twin turns around with his magical instantaneously going up the speed V rocket. Don't sweat the details here. And anyway, so at delta T over 2, he turns around there, all right? And so the proper time is given by this formula right here, and when you calculate it for Mr. The moving twin, right, the blue path guy, the proper time from A to B prime would be the square root of the time squared minus, here's the distance, which would be the speed times the time, yeah? And so you do the algebra here, and you get 1/2 the square root of 1 minus v squared times delta t. And so when you compare that, the traveler time, the time that went from A to B prime to C, is equal to the square root of 1 minus v squared times the stationary, the guy who just sat there. And it's like, wait a minute, you mean to tell me after this trip happens that one twin is older than the other? Yes, in fact, the one that sat still, the one that was on Earth, oh good grief, let me not say it backwards. Which one of these is longer, the traveler time or the stationary time? Well, let's see here, square root of 1 minus v squared is, so keep in mind here, c is equal to 1, I think, in this jibber jabber. So, so that means that this is the square root of a number less than 1, which is, what? That's less than 1, right? So this could be 0.5. So that means that if this was 0.5, that would mean that the traveler time was twice as long as the stationary time. So the guy who's moving stays young. The guy who just sits on his butt and waits for the twin to come back, he's comparatively older. And so this is sometimes called a paradox, because it's like, but they're twins, how can they have different ages? And of course it just ignores the obvious thing, which is that one twin moved and the other one didn't. And this paradox is made more troubling by the lengthy discussions of how motion is symmetric in terms of relativity. Like, you can't tell if A is moving or if B is moving, they're just moving relative to each other. You have this whole setup about the symmetry of motion, and then you give this example which is grossly asymmetrical and then complain that it's a paradox, which, I don't know, I don't care for it. So anyway, that's all I got to say about that. And this is just a warm-up. I will give you a more, we're going to talk much more about Minkowski space going forward. Anyway, I got to stop here for now. So thanks, guys.